Hello, my name is Kyle. I'm a third year studying computer science and mathematics at the University of Virginia.
Yeah, and I'm Jonathan Bierly. I'm a third year as well at UVA studying systems engineering. Our project is on classification of irrigation type, specifically from remote sensing imagery using multimodal deep learning.
We are advised by Nabir, Oishi, and Mandy. Our project is preliminary work in contributing towards Nabir and Oishi's overall project of mapping agricultural assets at scale. So our project identifies irrigation types. This is drip, flood, and sprinkler. This is essential for water resource monitoring, which is like optimizing water use for water scarcity, as well as agricultural planning. Our primary focus here is using remote sensing data. Satellite imagery and metadata provide scalable and cost-effective alternatives to ground surveys. Traditional approaches treat all of this data as pure numerical or categorical inputs. Our approach encodes this data as natural language text prompts to capture the semantic meaning of these features relevant to irrigation. This enables our models to hopefully interpret semantic and domain-specific cues from this language rather than just pure data. Current models fail to generalize to unlabeled states in different geographic regions. Our goal is to enhance interpretability and the generalizability of irrigation classification models, and eventually support large-scale, semantically informed agricultural monitoring across large, diverse regions across the whole entire United States.
Our dataset consists of satellite images segmented by irrigation type. We have these for a couple of states across the U.S., including Arizona, Colorado, Georgia, Washington, and Florida, with 1.2 million total patches that we filter down to just homogeneous patches. Our goal is to develop a pipeline and assess the generalizability to new states, which goes along with our general goal of building a national model. Our dataset is in balance with respect to both geographic and class distribution. You can see here that a lot of our data comes from Washington and Colorado, with very little from other states. And here that most of our data is sprinkler with a little bit of flood and barely any drip. Initially in our data set, our satellite images can be a lot of different sizes, so we first resize them to a consistent 224 by 224 for our image processing. On the text side, we have a lot of different features initially that we want to interpret, but our text processing has a limit. So initially we identify a couple key important ones. To find these features that are important for irrigation, we initially used random forest models and their own built-in feature importance index to find important features. Our top 5 features were retained, as you can see here, which are ET, evapotranspiration, groundwater, elevation, surface water, and precipitation to meet our 512 token limit. These were just our numeric features, but we have a couple other categorical features that we kept as well.
For our modeling pipeline, we experiment with frozen backbone encoders with a 3-class classification head. These encoders take in different inputs or modalities to generate distinct embedding representations for classification. So as you can see in our diagram, we utilize 3 different models. First, we use BERT as our text encoder. This is built upon a bidirectional transformer architecture and is especially used for natural language processing. Next, we use the SWIN transformer, which is a hierarchical vision transformer with shifted window attention. Finally, we use remote clip, which is our multimodal model that is contrastively trained as a vision language model for remote sensing.
To train these models, we minimize our loss, which is pretty much a measure of how wrong the prediction is. We use 50% cross entropy, which measures how well the predictions align with the actual, and then 50% focal loss, where it particularly focuses on hard to predict examples. On the graph on the right here, you can see those trends for all of our models, and you can see they all decreased over the time. And here are the metrics for each of our models. We mainly focus on F1 score, recall, and precision. Precision is a measure of the predicted positive, what percent are true positives, whereas recall is a measure of the actual positives, what percent were identified. F1 score is a harmonic mean of the two. You can see here that all of our metrics pretty much progressed as expected, with initial spikes and then plateaus towards the end.
So for our results, we ran two sets of distinct sets of experiments, in distribution and out of distribution. For in distribution, we train all of these different models on the single state and then test it on that single state. The train set and test set for these single states are distinct. And then for out of distribution, we train on all other states, then test on that one single state to see how it performs on this new distribution. From these results, we can see that the text encoder model, BERT, has decent performance on in-distribution results. And when we look at remote clip, our multimodal model, its performance surpasses both single modal approaches. This reveals that text-encoded metadata not only captures domain-specific patterns, but also semantic prompting through multimodal models can improve performance. As for our out-of-distribution results, when we do realize some limitations. We find that remote clip is always better than at least one of the single modal approaches, but it's rarely better than both single modal approaches except for Utah. The reason for this is cross-modal approaches might need more data for semantic generalization. Furthermore, when we freeze the backbone, we sort of hinder the multimodal training for how much understanding it can have of the data.
To conclude, what we really found is that the text modal inputs really serve as a viable point of exploration. They contain a lot of data and seem to really help the model, at least in distribution, predict irrigation type. For future work, though, we should really address that multimodal performance, either by fine-tuning more extensively, maybe using low-rank adaptation, sort of to improve that generalizability, or maybe experimenting with more data. We cut off a lot of features due to our text processing limit, but we could definitely try to find a way to work around that in the future. Once again, I'd just like to really thank the Biocomplexity Institute with Nabir, Oishi, and Mandy really helping and advising our work. And thanks again to AgAid for making all of this possible. And here are our references if you guys need any sources for our work.